Dr. Abhilash S., the Director at Advanced Center for Atmospheric Radar Research. Dr. Abhilash S. is the Director of the Advanced Center for Atmospheric Radar Research at 𝐀𝐻N Institute of Science and Technology, where he also serves as the Assistant Professor. With an MSc in Meteorology and a PhD in Atmospheric Sciences from CUSAT, he began his scientific career as a senior research scientist at Flagstone Reinsurance, Bermuda. He has held research positions at the Indian Institute of Tropical Meteorology and as a visiting scientist at the University of Miami and the National Center for Atmospheric Research, USA. Known for his contributions to high impact weather forecasting, he has received numerous accolades, including the SARC Scientist Medal, the IMS Award, and CUSAT's Best Young Faculty Researcher Award. Dr. Abhilash has authored over 90 peer reviewed publications, 16 books and chapters, and has conducted extensive outreach on weather and climate sciences in both popular media and public lectures. It's our esteemed honor to have him with us today to share his insights on the role of technological advancements in reducing uncertainties in weather prediction today. We welcome you, sir. As we commence, I would like to welcome Ms. Anjal P. Dijo, student representative of the IEEE Education Society Kerala chapter, to deliver the welcome address. Over to you, Ms. Anjal.
Good evening, everyone. We are incredibly honored to welcome our esteemed speaker, Dr. Abhilash S., Director of the Advanced Center for Atmospheric Radar Research, to today's Pro Talk session, episode 7. I warmly welcome Dr. Abhilash, whose expertise in atmospheric science and weather prediction is widely respected. Welcome, sir. We are thrilled to have him here to share his insights on the role of technological advancements in reducing uncertainties in weather prediction. His knowledge and experience will undoubtedly provide us with valuable perspectives. I will also like to extend a warm welcome to our enthusiastic audience of professionals, participants, and IEEE members from various chapters. Your presence reflects a shared commitment to learning and advancing knowledge in this field. Thank you once again, Dr. Abhilash, for joining us. Wishing everyone a productive and engaging session ahead. Thank you.
Thank you, Anjal. Now, it is time to invite the esteemed guest of the hour, Dr. Abhilash S., to deliver his thoughts to our August gathering. Over to you, sir.
Yeah, thank you. Thank you very much for the invitation to interact with the young and vibrant minds for the future. So, without much introduction or remarks, I will straight away go into my presentation. I'm sharing my screen. I hope the screen is visible, right?
Yes, sir. The screen is visible.
Yeah. So today I will be talking about the role of technology in reducing the uncertainties in weather prediction. Actually, the meteorologists, the weather prediction community have benefited from the technological advancements in many fields. So what we realize today as very reliable prediction, it is because of the technological inventions which happened in almost all fields. So yeah, we know that the climate change is the reality. So I am not talking about the climate change, but some kind of impact of climate change, because climate change is mostly realized in terms of increasing global temperatures and altering the and increasing the sea levels, and also altering the hydrological cycles by, because yesterday also we have witnessed very big flooding in Spain, which is like the annual rainfall is received in just 24 hours. So that is how the climate change is changing. So that is a reality. So according to that, basically these are some of the parameters we realized in terms of climate change. So it has got a lot of impact in the weather, whether it is changing due to global warming, the weather pattern all over the world is being changed, and there's a lot of issues related to water. Because if you look at the look for the future, there are three nexus through which we have to have a lot of sustainability, because that is water, energy, and health nexus. So where we have to invest more, and also air pollution, air quality is reducing. The yesterday's air quality in Delhi is almost like air quality index went up to more than 300. So then the ecosystem, the natural habitats around us is changing. So that also has a lot of impact, because best example is COVID-19 pandemic. So the man-animal conflict and a lot of virus is being transferred from forest to human habitat. So these are some of the effects of climate change. And here, if you look at the disasters, as I told yesterday, the Spain witnessed, and 1 week back, Orissa and Bengal, they witnessed a very severe cyclone, Dana. So there was not much casualty. That also we discussed later, how we reduce this casualty. So there are a lot of impact, but overall the disasters are increasing. So how to adapt to this situation, and also in long term how to mitigate this. So the climate change related hazards, we know that rising, already I discussed about this. Ocean pattern is very complex, that I am not touching in this half an hour. But there are how to respond to this climate change, because loss of biodiversity, on the other hand, impact on agriculture. So this together will affect the food security. If you look at the sustainable development goal number 2, um, uh, reduce the hunger, and also the sanitation and the food security, everything is also needs to be addressed in terms of climate change, because this all biodiversity and agriculture system is getting affected. So that means, and also the health sector, that is also very another, because there is no it is not just about the physical damage to our health system, but the mental issues connected to this is also to be addressed. And then the social, there are a lot of socio-economic issues connected to climate change, and also then climate migration, and is very large issue, because if you look at the global migration statistics, we can find that people are migrating because of extreme weathers, and also due to war. So maybe more than war, the people are migrating from one place to other place due to adverse climate impact to their socio-economic means profile. So where if you look at the climate related risk, if you look at the risk equation, we can find that risk is a combination of the hazard, vulnerability, exposure. So where we have to discuss about the vulnerability exposure part is related to how our people asset, and it is actually geographical and the socio-economic exposure. The vulnerability is decided by socio-economic factors and also geographical factors. So apart from that, hazard itself, earlier there were a lot of heavy or climate extremes were happening around the world, but now the thing is that the frequency and intensity of this extreme is increasing. So that means if you look at the risk directly, the hazard intensity and frequency is increasing. That means the risk itself is increasing. So there is a disaster paradox. If you look worldwide, the decadal evolution of the number of disasters are increasing. And if you look at the death rate, this is decadal average death rate, it is reducing. So this is a clear and very promising signal, though climate change is there and the disasters are increasing, but we can able to limit the fatality or the death associated with the disaster. This is mainly because of the our investment in better early warning system. If you look at this is 25th year of Orissa big super cyclone, which happened in 1999, around 25 years back in Orissa. So where it took almost like more than 10,000 people's life. Even if you look at the Bangladesh history in 2005, one cyclone killed almost like 1.5 lakhs of people. So that is because that is why from Bangladesh, lot of migration is happening to India and Myanmar. Or this migration is connected to, not only connected to other racial or any other political dimension, but that also somehow linked to climate impact. So this is how we are able to limit that 10,000 death to zero casualty or zero death. If you look at the recent severe cyclone Dana, it went up to Orissa Bengal border, and we are able to evacuate almost like 4.5 lakhs of people from the coastal belt, so that we reduce the impact of this. That is because of the good warning system we are now in place to save the life of the people, and also to some extent the properties as well. Because if you look at the Orissa story itself, we can find that a lot of activity they have initiated along the coast to reduce the damage from high wind and storm surge. So that is due to combination of nature-based solutions and those technological-based approaches. And here I will be mostly talking about the early warning systems, how to reduce the risk. We cannot stop a hazard coming our way, but what we can do best is that we can predict this well in advance, so that the casualty or the death rate can be reduced. So the earlier traditional approach was, when a disaster is coming, our response is that when it is coming on our way, we are trying to escape from that. But now the enhanced approach is there is a good early warning system, so that we can take early actions. Maybe one day in advance, we can evacuate 4 to 5 lakhs of people to avoid any death during the disasters, because any hazard becomes disasters when there is a lot of death associated or the damage associated with it. Can limit that so that hazard will end up with just hazard only. But when it becomes disaster, like for example the Wayanad Mundakai event becomes the hazard becomes disaster because of many factors, because of our there are a lot of issues. I don't want to mention all these things here, but otherwise, then the good response capability, that is where the government mechanisms should be. Even though if there is early warning is there, but if government mechanism or the people living in that hazardous area, if they don't have that response mechanism to respond to this early warning, then it will end up with, even though with a good type of early warning, it can end up with disaster. So it's a kind of if you want to reduce the death associated with a hazard or the disaster, there should be good mechanism to at the ground level to which is actually responding to the hazard, where a lot of technology is also required to in this dimension, like geospatial engineering solutions or the geospatial analysis. Everything is required in reducing the damage. So if you look at the forecast, coming to the forecast, the forecast is nothing but, if you look at the weather system, there are different type of weather system which has got their characteristics, length and time scale. Because if you look at a single cloud system, it will come and go in about 3 to 4 hours. So if you look at a cyclone, the normal time range of a cyclone is 4 to 5 days or up to a week. So that, and the aerial extent of a cyclone is thousands of kilometers. So that is a very bigger system. Cloud is a very smaller system. If there is raining in Edapalli, we won't get any rain in the Vaitila or Kundanur. That is what the cloud systems are, very localized systems. Their time scale is very short, and the length scale, the aerial extent is very limited. But in the case of cyclone, it is larger. And if you look at the monsoon is a very larger system. It starts from the southern hemisphere all the way up to South China Sea. It covers almost entire South Asian belt. So the monsoon is a very large system. So that means these are the some of the target in the weather prediction we have to look at. So it is weather prediction is actually like a shooting problem. It is like the range is that is the shooting problem. Depending on the target size and the range of this target, we select some kind of tools, weapons, according to the size of the target and the range of the target. Likewise, if you look at the weather prediction problem, it is like a shooting problem. Target is weather features. So the cloud is one target. Like for example, in a shooting problem, we will select a rifle for shooting a rabbit at a range of like 50 meters. But the same rabbit, if it is at a range of 500 meters, cannot shoot with a rifle. We have to use another weapon or tool. Likewise, if a cloud system, we can use a strategy, and if it is a tropical cyclone, we use another strategy. The tool, we use different tools. Like that, it is actually a very complex process. We have to determine which type of tool we have to use to aim the target. So likewise, there are different type of ranges of forecast. Like for example, for the shooting range, short range, medium range, long range shooting. So like that, the weather prediction is also like depending on the time scale and the length scale. We divide each ranges of forecast into different categories. Like short time forecast, it is known as nowcasting. What is happening in the next 6 to 12 hours? That is, and within few kilometers, that is the nowcasting. What is going to happen just now after this moment? So that is what the nowcasting. It is not forecasting, it is nowcasting. What is going to be in the next 1 hour, 2 hour, like that. So that there we use a radar, satellite, and a combination of models for predicting this for nowcasting. And then short range forecasting, it is the time range is 12 to 48 hours, up to 2 days, and the length scale is like tens of kilometers, where big cloud system is our target. The medium range, as I told, 2 to 5 days. Mostly the cyclones are the main target in the medium range. The weekly scale, the monsoon system, which is very large system. So there, monsoon, intra-seasonal oscillation, active, extreme weather events, extreme rainfall events, extreme rainfall spells. These are these targets in the sub-seasonal range. The weekly, 1 or 2 weeks in advance, we have to predict, and it covers almost like thousands of kilometers. And seasonal prediction is like monthly scale, monthly and more than 1 month. That is seasonal prediction. That is for the monsoon, the entire monsoon system over the India. If you look at this is just an example. This is if you want to predict the clouds over Cochin, it should be it is possible only in the shorter range, like nowcasting scale only it is possible. And if you want to consider large systems, like very large area covering system or covering that is should be addressed in the short range time scale, up to 1 to 2 days, and then the 3 to 10 days, very large, slightly larger area, which is attempted in 3 to 10 days, and very bigger area we have to attend in the monthly or seasonal scale. So this is how the scales are. So that is what it is like a um, uh, it is like a 100 meter relay or something. So there are different cascading of activities. So it is like a get, set, go. The seasonal prediction, where what is happening for the season, there is a prediction for that. And when it is coming to the weekly prediction, it is a kind of setting the things. And then when it comes to short range prediction, there we have to take the action. So that is what watch, warning, and alert. So that is what the different scales of activity is. Also, this is just an so then there are different, as tools are different, but there were many forecasting strategy we use earlier times, like persistence. Persistence is a very simple method of forecasting, where we persist the weather for today for the tomorrow, because whatever weather, especially during monsoon season, if we are getting rain today, naturally we can expect rain tomorrow. So that is what if you persist the today's weather as tomorrow's forecast, it is almost like 70-80% accurate. It's a very crude method of forecasting. Then climatological forecast is like, we can say that monsoon is arriving over Kerala around 1st June. So that is a climatological forecast. I am predicting that next year also monsoon is coming around June. 1st June. So that is a climatological forecast. We can expect maybe by the end of May or 1st week of June, we can always expect the monsoon. So that is based on climatological forecast, trend forecast, analog forecast. Then now I will discuss mostly on the numerical forecast and the ensemble prediction, because things are very much advanced. We are going from the skill of prediction earlier, maybe before 1980s, skill of prediction is this type of prediction skill was higher compared to numerical for weather prediction. But now numerical weather prediction forecast skill is improved a lot. So that is why our prediction tool, earlier prediction tool from the Quacking Frogs to advanced prediction models using high performance computing and supercomputers. Using satellite data, radar data, different type of data sets, we are able to, our tool has been changed. And if you look at the skill of the prediction skill, these are the, so if you look, this is 3-day forecast means short range prediction skill, 5-day forecast means 5 to 7-day medium range forecast skill, 10-day forecast is a subseasonal forecast skill. If all from 1981 onwards, if you look at the skill of the forecast, all ranges of forecast skill is increased a lot, because the 3-day forecast skill was around 80% in 1981, but it becomes 99% by 2018. So the skill of forecast 10-day forecast is only 20% in 1981, but now it is almost like 50%. That means it improved a lot. 7-day forecast skill around 40% in 1981, but it improved like 70% by 2018. That means this much improvement we have noticed in our weather prediction skill. That is mainly contributed from 3 factors. One is the improvement of weather prediction forecast, which is coming from high resolution of this numerical weather prediction models, which improve with improved representation of physical processes. That I will discuss briefly. What are the physical processes, and then due to the increase in the quality of the meteorological data, which is coming from satellite and radars, and also advancements in the telecommunication system. Because if you look at the weather prediction, we need to have a bird's eye view of the entire globe at same instant. So that means if we want to predict the weather over India, we need to know the weather over Pakistan, Afghanistan, on the eastern side, China, Japan, all the Pacific region. So that means each country has to share their data among other countries to make good predictions. So that is why telecommunication system is very much important in sharing, timely sharing of the data between the across the national meteorological center. That is through advancement in the telecommunication system, weather prediction has advanced. And then another main factor is the NWP. The numerical weather prediction is nowadays is being done with a high-end computing system, high performance computing system, including supercomputers. So that means these are the 3 main factors which is contributed to the improvement in the weather prediction skill. We'll discuss a little bit more on this, like the major steps in the weather forecasting. We have to have the data, and we have to control the quality of the data, quality control, and then data assimilation, model integration. All this process we have to do. So in a nutshell, what we are doing is that we in a NWP, numerical weather prediction system, what we to address is the forecast of any parameter, any variable at a future time. It is the variable of that the value of that variable at present, plus the change in that variable. That means what are the forces which is making changes in f in a small time step. So that is what that forces, if you know, to make the changes in that particular weather variable for a small time step. So then we can predict. So then the next value of this variable will be the initial value of f, initial value of this variable, plus dou f by dou t in delta t time. So this is delta t. We have to convert all this partial differential form of equation to finite difference form. That is why that delta t is coming. So the meaning is that if we want to predict a variable f at a location, x is location at t plus delta t at time now plus delta t time. Next time step, it is the f of that variable, the state vector at t time now, the initial time, plus 𝑑𝑜𝑓 by 𝑑𝑜𝑡. What are this 𝑑𝑜𝑓 by 𝑑𝑜𝑡 is very much important. So how this variable f can be temperature, pressure, humidity, wind speed. So how the temperature over a particular location will change? What are the forces which making changes in temperature in that short delta t time? So that is what we have to look at. This is a simple nutshell or simple explanation of NWB system, how it is possible weather prediction. So this is a complex activity involved in this, and weather prediction is constructing a numerical weather prediction model. It's a very big task. It is actually, we have to consider the entire globe. We consider and we divide, we discretize the entire globe into small grids. So it's like a pixel. So here the pixel is size is like 5 kilometer, 10 kilometer, 100 kilometer. So that based on that grid cell, we have to construct this model. All these models, NWP, numerical weather prediction models, are based on conservation laws, because physical laws. So because the models are mathematical model, so it is like a not like a physics means uh, other type of modeling. It is actually the models are based in mathematical equations. So these mathematical equation, this governing equation, which is formulated based on fundamental physical laws, which is nothing but we know that conservation of momentum, conservation of energy, conservation of mass, along with equation of state. That describes the entire process of the atmosphere. And if you can solve this equation, these are some of the forecast equations I have shown here. If you can solve this equation perfectly, then we can predict the weather for the future time. So that is what the equation. But here there are few unknowns and uncertain things given here. This is why, because if you look at the temperature change, the temperature tendency, temperature forecast equation, this is contributed from advection, that is due to advection carried by the wind, and along with the H by Cp, that is the total diabatic heating. So this total diabatic heating, the H term, that is the main non-linear term, unknown thing, which is due to many processes happening in the atmosphere, real atmosphere. Like for example, cloud processes, convection processes, radiation processes, small scale processes. These all processes we don't know, 100% we don't know. So that is why we have to represent in our equation all these processes which is not known actually reliably, and exactly we don't know. We know bit and pieces, but exactly what is happening here in the real atmosphere is not known to us. Thing is that in a weather prediction model, we have to represent all this net effect of all these processes in the forecast model. So that is one challenge. That is the one challenge of numerical weather prediction, is representing the unknown processes in the atmosphere with empirical or any kind of equations in the model. That is why, since due to this unknown nonlinear term only, we cannot come up with a exact analytical solution for this. That is why we have to depend on numerical solution to solve this equation. So if is perfect, we can give a perfect forecast, but we approximate to numerical approximation. That is why, and for that, as I told, we for forecasting any variable for the future time, we need to know the value of that variable at the initial time, the current time t, then plus delta t time, what is going to be changing. So that with this parameterization of physical is also important. So initializing, that is what we call as initializing this model. We need to give data, because with the data only we can initialize. We have to initialize the model at each and every grid point across the globe. So that is the another issue, because if you look at the globe, some part of the globe is ocean. Maybe 70% of the surface area is ocean, and the polar region like Arctic and Antarctic, there is no observations. So but in a because each grid cell is talking to each other, there is lateral connection between the cells, grid cells. So we need to, because this entire grid cell is connected, so that means we want to predict one grid value of any variable in one grid, we need to know the value of variable in another grid as well. So that is why it is everything is connected. So it's that is why for predicting values of the variable at other grid points as well. So that meaning is that we have to represent the data at each and every grid points. That data is the initial data, that initial value we have to give to this forecast model to predict for the future. So that initial condition. So that initial condition is not available everywhere on the Earth surface. That is another challenge. So that means we are dealing with the two uncertain things. One is unknown process in the model, in the equations, and another on the other side, we don't have sufficient data to represent at each and every grid points. So we are dealing with two uncertainties, but anyhow, we have to predict for the future. So that is why knowingly we are doing a job with a lot of uncertainty. So, and if you look at what is that physical uncertainty, if you look at a grid point, inside the grid point, we can say like rain, snow, and all is happening. So, but we don't know what is happening in the real atmosphere. So that entire representation of this has to be given in this term, this equation. So this is how one snapshot of that. And in a nutshell, we can say that in the real world, all these nonlinear processes are interacting each other. But in the model world, when we construct a real world, replicate it with the model, it looks like this, entirely different. We can approximate with this, that nonlinear process exactly we cannot represent. That is what the meaning. So that is why for the prediction, we need to know the bird's eye view. We need to get the data from everywhere from the Earth's surface. So that is why there are a lot of global cooperation is required for weather predictions. That is why this is coming under UN. This is known as WWW, World Weather Watch. This under this program of United Nations, we are sharing. Each country is bound to share their data to other countries through GTS. So that is why in a weather prediction, we need global cooperation where there should be a global observing system, which is nothing but this observing system. There is a wide heterogeneous observations available, but that is also not enough to initialize out the model. So that global observing system is important. And then this observing system, it is taking data and it has to be transferred to other countries through GTS, global telecommunication system, and that will go to each country's global data processing and forecasting system. So that data management is done through WMO, World Meteorological Organization, that is a UN body, through which we have a World Weather Watch, and in which there is a global observing system, and that observing system which take the data which is being transferred to GTS. Or if you look at this slide, a lot itself, if you look at weather prediction, there are a lot of technologies involved in each and every part of this. So that is why the weather prediction skill is improved because of the advancement in technology. So this is a global observing system. So the recent advancement, there are more and more, because this Elon Musk also is there. So he may come up with some solution maybe in the future with a wild guess, but I won't think maybe in 10, 20 years solving this issue is not a easy task, like sending satellite to the space. So it is more than that. So even Elon Musk, if he wishes, it is very difficult. If it is happening, it is good. A little bit of history of this numerical weather prediction. So it started in actually late 1900 by 1890s. But the first step in numerical weather prediction, that is done by Richardson. He was a famous scientist. So he tried to solve this equation and predict for the future. But that time there is no even small computer. He done all the calculation with his hand calculation. So he visualized a forecast factory, like he is the charge of that supervisor, and then it is like a stadium at different levels. People are working. He estimated like for producing a 6-hour forecast over the globe, it is almost like 64,000 manpower is required to produce a forecast for the near future. So that is very tedious job. So then from 1900 to almost 1950, up to 1950, the progress in numerical weather prediction is very slow, was very slow. Though he tried to predict, but he miserably failed due to many reasons. So that we will discuss later if time permits. Otherwise, up to 1950, it was very slow progress. And then by 1948, Charney, Joff, and Newman, they transferred this numerical models to a computer-based model. So that is a computer scientist. So actually, this is done in ENIAC, first computer system, like first electronic numerical integrator and computer, which installed in Pennsylvania, USA, for not for weather prediction. Look at in Second World War. That is the time when most of the technology emerged. That is why US taken over the Germany in in war because of the technology. So that is why, due to that technology, we have benefited. After the World War, 1950, we got a space in this computer. Charney, Joff, and Newman, they produced the first NWP numerical, computer-based NWP numerical weather prediction. So this is the picture of that ENIAC mission. It is a lot of many meter room for just for one computer. So now this entire room computer has been integrated in a small chip. That is why the technological advancement. So just the clock speed of this was 100 kilohertz. Now we have a computer with 4.2 gigahertz clock speed. So that is what the technology. Now our weather prediction is being done with supercomputers. If you look at the most world's famous top 500 list of supercomputers, most of the supercomputers in the world top 500 list, it is being 50% of the supercomputers is being used in weather prediction now. So if India is also not an exception, India's two supercomputer is also coming, but the position is 132. The Pratyush, which is having a clock speed of 3.8 petabytes, and Param-Siddhi from CDAT, it is 4.6. But now with our this is the latest rank from India, Param-Siddhi with 4.62 petaflops, and Airavat also from CDAC, it is almost like 8.5. So recently, our Prime Minister announced the mission Mausam. In that 2,000 crore project is being funded to advance weather prediction. So in that, if I means Ministry of Earth Science installed two systems, like two high performance systems like 𝗏𝗏 and Arunima, it is almost like 22 petaflops. So that means in the next cycle of top 500, this 𝗏𝗏 and Arunima is going to be replaced, means going to the top from India. And if you look at the radar, there are a lot of not only is increasing, and there are a lot of radar-based observations are coming. And if you look at the remote sensing, this is the famous 𝗏𝗏𝗃. He is considered as the father of remote sensing in India. Father of space science is Vikram Sarabhai, but father of remote sensing in India is considered by 𝗏𝗏𝗃. That is why you look at the radio sonde. We are launching radio sonde to measure wind speed, humidity, temperature in the vertical direction up to 20 kilometers. So in that we are attaching a sonde called 𝗏𝗏𝗃 sonde. This is developed by ISRO. And the 𝗏𝗏𝗃, what he did, remote sensing application was first detection of coconut wilt root disease detection. He detected to aerial photography. So the remote sensing is coming, and remote sensing through various platforms. Now drone-based remote sensing is also coming up, because drone-based aerial mapping and weather observation is also coming up. So that means remote sensing aided lot the technological advancement in terms of advanced sensors, hyperspectral sensors, and advanced remote sensing platforms and all. We are able to generate more accurate and reliable data. So it's the science behind this. We are using different type of radar. Radar is also, earlier we were using radars to just detect the object. Now with the modern technology like dual polarized radar, they have both horizontal and vertical polarization. With that, we can estimate the structure of the cloud itself. What is the cloud size, cloud particle, whether it is liquid particle, solid particle, size of the particle. All these things we can determined from the weather radar with a dual polarized capability. So that is also a advanced thing. And then now our data set is increasing. So our weather prediction skill is improved due to different type of variety of the data is coming through different platform, through technological advance, sensor based technology and sensor and the satellite based platform, drone based platform. There are plenty of data is being generated every day, and this whole data is being utilized by the weather models. So that means there are 4 V's of data, 4 V's. Earlier it was 3 V's. What are that? V's are the high volume, high velocity, high variety of the data, and the veracity. Veracity is nothing but it is connected to the uncertainty part of the data, the climate data. So that means in terms of other field, it is 3 V's, but in our weather prediction, it is 4 V's. This data set is increasing day by day, and the size of the data, it is estimated like now it is 72 petabytes of storage volume. Only the satellite data storage volume from NASA satellite alone. There is ESI, means European Satellite Agency, 𝗥𝗏𝗃, Japan Satellite Agency, and ISRO. All this data comes together, it will be going to be like 3 times this. And the NASA satellite alone is occupied by 72 petabytes by 2022. The projected to be like 600 petabytes by 2030 with the modern satellite missions. So this is how plenty of data is coming every second. So we need to address this. Actually, weather prediction is actually going to be a kind of big data problem. So where various sources of heterogeneous data is coming, we have to assimilate all this data is coming from different sources. We have to optimally utilize this. There is a data assimilation that is based on the optimization through variation assimilation schemes, ensemble Kalman filter, and also nowadays AI-based assimilation schemes are also there. So, and our model itself is getting more complex. We can represent more and more processes in the model. Earlier it was just ocean, then land, atmosphere, seas. Likewise, this from 1890s from radiative transfer model, just a simple zeroth order model to high dimensional models are. Now our models are considering chemistry, carbon cycle, socio-economic factors as well within the model. Earlier time it was just atmospheric process, then ocean is integrated, then land is integrated, then sea is integrated, and then sea ice is integrated, then aerosol is integrated, and then greenhouse gas integrated, then biology is integrated, then geochemistry is integrated. Like that, every year our models are getting improved and getting more complex, and all processes is being integrated to our models. That is the main thing we approach. We are able to make good predictions for the future. So this is how there are 2 sorts of uncertainty we have to deal with. That is, one is from the initial condition, that the data uncertainty, and another is the model uncertainty. I already discussed representation of this unknown physical process to our model. So that too contribute lot of source of uncertainty in our final forecast. That is why our forecast is always failing in the sense that we cannot make a 100% accurate forecast, but we can give up to like 70-80% accuracy. But with that accuracy, that is very useful. That is why we limited the death rate from 10,000 more to nil from 1919 to 2024. That is where though we cannot produce a 100% accurate forecast, the 70, 75, 80% accurate forecast is enough to reduce the risk. That is what I want to convey here. So that means there are a lot of uncertainty. If you look at just uncertainty, just an example, you can see that two balls which is very close to each other, which is falling from a waterfall. If you put the two balls exactly at the same point, but after, if you look at the trajectory of these two balls, after some time, one ball will reach here and another ball will reach here. So both the balls are being dropped at from the same location. And you again take these two balls, the same two balls, you take and again drop the same position, but that will be some at some other random position. The first ball will be somewhere here, other ball will be going somewhere here. So this is the uncertainty. So we are dealing with the uncertainty like this process uncertainty, we don't know exact, and answer for this problem is also don't know. We don't know why it is happening. So that much uncertainty is there in the physical space of the weather. So that is why we have to deal with this uncertainty. So where we can do, because that is why will follow like a trajectory which is known. Then it will follow like a random trajectory after few hours or few days. So that is why if you look at that random, whether there's two attractors or which this is the solution will be moving around. So that is why the shape, considering the shape, it is known as it is almost similar to a butterfly. It is not like that a butterfly flattering of a butterfly in Mexico can create a tornado in the Texas. It is not like that. It's actually representing the uncertainty, a small uncertainty in the future. So that is why why that is where we need ensembles of forecast. If you look at this forecast, this is the trajectory of the 12-hour forecast. Forecast trajectory is going like this, 48-hour in short range. It is coming here. But if you look at the real atmosphere, the real verification in the real atmosphere, after that it is coming here. So the error in this forecast is this much. This is our forecast value and this is the actual value, this much error. So how we will address this? So this change is because initially this trajectory is very closer. After few hours, it is very diverging a lot. So that is what that as the time step increases, the forecast uncertainty it increases. That is where we run with insert. This is the two. One is a true value and another is a forecast value with only one deterministic value. But if we look at run with ensembles of forecast, then we can say that some of the ensembles which is being perturbed slightly from the initial condition, that will be closer to our value. Few of the ensemble will be closer to the observed value rather than the outlier of like the actual one deterministic value. So that is why the meaning of ensemble. So likewise, part of this uncertainty as the time step progress, this is being addressed with ensembles of forecast. This is a modern technology which is being used for addressing this uncertainty. So there are a lot of nowadays in India also we have developed this type of ensemble prediction system through which only we are giving this cyclonic forecast. And now the AML is coming in a big way to address the observational data assimilation, numerical forecast, the physical parameterization, then post-processing of the model. All this AML is going to be a big game setter, but it cannot address the physical processes. That is what the physical process, it will not improve much, but thing is that with AML we can optimize much better. That is why AML technique will not solve everything related to weather prediction, but we can optimize certain things at each and every parts of this the process chain of NWP. And then this quantum computing is coming. So that also expected to improve weather forecast maybe in another 10-20 years. So that is why we are progressing. There are a lot of technological advancement happening in terms of climate change also. So if you look at the technology cycle, that innovation, the rapid advancement nowadays in the sustainable technology is very rapid. The meaning the electrification to space age took around 15 years, and from space age to digital around 10 years. But now technology is advancing every day, every instant, new technology is coming up. So all this technology is being utilized for our field, and that is going to be for the better future, like for early warning for all. So this is where some of the example I am even with the Mundage event. This was the prediction in the real time we have issued. It's a 3-day advance prediction for 𝗏𝗏𝗧𝗏 2 day and 1 day. So there were enough prediction for that Mundage event, but this is not being utilized properly by the agencies. So we can integrate this our model, landslide, flood warning, and everything we can integrate. And what I want to say here, there are, as part of Sustainable Development Goal, goal number 13 is climate action. So that is integrating all this. That is the main pillar of all sustainable development goals, through which we have a lot of opportunities, a lot of challenges, and we have to address the mitigation strategy, mitigation options like clean energy, low emission technologies, low emission industry, sustainable transport. Everything is technology based, and also the adaptation based, like emergency disaster management and the early warning system, more better early warning system. So the synergy between mitigation and adaptation should be there. We have to invest more in these sustainable solutions, and even in the climate smart agriculture. The motto of climate smart agriculture is to enhance the productivity, enhance the resilience to climate shocks, and then reduce the emission in a mitigation strategy. So there are a lot of robotics applications and IoT applications, and then the drone based application is coming in a way to solve all these things. And so there are a lot of challenges. So this is a real time forecast, because maybe another one system in we are expecting by the 3rd week of November, that also brings some kind of rain, very extended range of predictions, where this type of, that is what the get set go, getting information for 2-3 weeks in advance. So this is the week, the 3rd week, where we are expecting some kind of system in the east coast that will bring some rain along Tamil Nadu, Kerala region. So this is how we can utilize the model. All models are wrong, meaning we cannot produce a 100% accurate forecast, but it's 70-80% accuracy is enough to reduce the damage. So that is the meaning. All these achievements we have done through different advancement which happened in the different sectors of the technology. So I think this is time to stop. Thank you.
Thank you so much, sir, for an insightful hour on how technological advancements are transforming weather predictions on and how we can reduce uncertainties. And I'm sure all of us gained valuable insights into harnessing technology and understanding that on helping us address modern day climate challenges with confidence and precision. Now, let's move on to the Q&A session. Uh, I request all of you to kindly feel free to unmute yourself or make yourself available through the chat box for any queries regarding the topic or in general to our speaker.
Good evening to everybody. I am 𝗀𝐻𝗧𝗏. Am I audible? Am I audible? Yes. See, before I ask a question, first I would like to advise our young friends, such an important topic. And when professor said accuracy is not 100%, accuracy is 70-80%, all models are wrong, and what are the new development which is coming up in the next 10 years, even 20 years he was talking about. That shows there is lot of research opportunities for you to join him or any department anywhere else in the country also. So that should be natural curiosity. This is an open challenging area. A lot of improvement is required, means lot of effort is required. That means lot of talent is required. I think why not we get into asking him some questions and getting into a discussion. And with this trigger, if anybody is asking, I will wait for that. Otherwise, I will ask. Professor, for your information, I am an advisor to Education Society in Kerala, and I am an ex-TCS person and ex-ISRO person. So, in
Oh,
fact, I
nice.
had in remote sensing also.
Oh, thank you, sir. Thank you for joining. Thank you.
Yeah. No. It is important, sir. The area what, see, for example, I tell you what Professor is covering is very, very important. Last year in Solingam Road, Chennai, my daughter lost a few lakhs car, totally out, right? And again, as Professor, of course, obviously we cannot talk politics here. He talked about two challenges. One is data can be inaccurate. Other one, moral inadequacy. These two challenges he said when he was predicting. I will say, of course, though it is little touching upon the politics, I will also say the executive's acceptance of the advice and public preparedness and public responsibility of carrying forward the advice given by the scientists. I think those two are also equally important factors in mitigating the risk.
Yes, yes.
Obviously, Professor or me cannot be more explicit than this.
Yeah. Well, there are
Yeah.
still politicians and people there still asking that why ISRO is spending money in space space-based technology. So they are not even realizing that their life is getting better due to ISRO's. Yes.
No doubt. Since some of these youngsters, they will have the research mindset. Possibly, with my trigger, I will still wait for them to ask questions. And I have a question, Professor. Yeah, at the end, yeah. Knowing all the current limits, years back, I also had tried for a metallurgical department job and ISRO and National Geophysical Research Institute. NGRI and ISRO I got. The metallurgy department I did not get. I chose ISRO. So my question I will reserve till our friends ask. Who is coordinating this event, Ma? From our side, from IEEE side? I think we should speak. Who is coordinating from our side? Pardon? Hello? Your voice is breaking. Any of you having questions? I think these are all important opportunity. What education society brings you is very, very important. Sir, my question is this. A couple of years back, of course, when you talked about challenge, I will give another challenge. The globally connected world. 2-3 years back, there was a published news item. I don't know whether it was in the research journal or popular publication. The excess bushfire in Australia was linked with excessive rain in India, in some parts of India, unusual excess rain in. Have you seen that news item, sir? Otherwise, I will try to locate.
I have not exactly know this, but I connected to that. I can give some comments on that because the weather around the world is interlinked. There is a lot of teleconnections, and maybe the bushfire in Australia is triggered with El Nino situation. So that El Nino can severely affect our monsoon. So and our monsoon and also the rainfall, excessive rainfall at some other places. It may not be the direct impact. It may be due to the indirect impact of transporting pollutions and transporting many things through altered circulations. There is a lot of global circulation is there. So El Nino can alter or relocate this circulation, clusters of the circulation and nodes of the circulation. So that will cause. So that means it is not like a chicken egg problem, but it is interlinked and interconnected. Yeah, that is known as teleconnections. It is always there because Australia rainfall is also linked to Indian monsoon and all.
Okay.
So if there is no more questions, we can wind. I have to join another meeting. Sorry. Nice to meet you, sir. Yeah, thank you.
Thank you, sir. Thank you. I really loved this. Thank you. Of course, it was challenging for me, but still I like.
I hope
Thank
our
you.
young friends digested.
Yeah, yeah. But you made it understandable.
No,
Thank you.
I made it a lot of challenges in front of them, and they
Yeah.
don't need not be like a weather forecaster, but their contribution in the technology can also improve the weather forecast. That is what I want
Absolutely.
to, I
And
want to
AI,
say.
ML, lot of
Yeah,
computer
yeah,
scientists,
yeah.
data analysts, a lot of job opportunities there. Whatever.
IoT,
Yeah.
drones, everything is contributing to our
Even remote
future.
sensors, everything.
Sensors, advanced sensors, hyperspectral sensors, all
Yes,
is,
sir.
yeah.
Thank you, sir.
So, so we had one question from the audience. Would you be able to answer the same? We have a question from Adil. He has asked how ISRO is supporting startup companies.
That
So I
either
am,
him
I
or
am,
me cannot answer. Yeah.
that is not in my domain because I don't know anything about
Okay.
But
Okay, sir.
1 minute, I will ask one, I will answer. See, there is one program in ISRO called Respond that has close collaboration with the leading academic institute like IITs. Maybe some incubation centers are also supported. I don't know. Please check with the Respond program. And post this meeting, I will check with some of my ISRO friends what kind of support system they have. You mean student community, right? What was
that.
the question?
So it was a
Startup,
general
startup.
question.
Startup,
Startup.
startup, yeah, young startup. Okay, I will check with friends. Thank you.
Thank you, sir. I hope all the queries have been answered. Um, I would now like to request Anantakrishnan KP, the technical coordinator of the IEEE Education Society Kerala chapter, to please do the honors of capturing this memory for us through a virtual photograph. I request all of you to kindly turn on your cameras and give me your best smile for the photograph. Thank you. A feedback form will be shared in the chat box after the vote of thanks. The certificate will be distributed based on the same. As a token of our appreciation, sir, we would like to present you with a virtual memento. And for that, I would like to invite Mohammed Sultan, the newsletter editor of IEEE Education Society Kerala chapter, to share the screen and present the virtual memento.
Thank you very much.
Thank you. At last, and not the least, I would like to invite Sanya Teresa Sandeep, the Membership Development Coordinator of the Travancore Hub of the IEEE Education Society Kerala chapter, for delivering the vote of thanks.
Finally, we have come to the end of this thought-provoking session of IEEE EDSA Kerala chapter presents Pro Talks. First of all, I would like to thank Abhilash sir for being here today with us to deliver this amazing session. We really appreciate your time and effort, sir. I would also like to mention Dr. 𝐀𝐻𝐿𝐴 sir for gracing us with his presence. Next, I would like to thank all the distinguished members of the professional lexicon and student leadership team for coming up with this wonderful session. And finally, I would like to extend my huge thanks to all the participants for their active participation in the session. Once again, I extend my heartfelt gratitude and thank you.
Thank you. Bye.
Thank you, Sanya. Thank you, sir. Thank you for your presence. And with that, we conclude our session. We hope all of you found it valuable and enjoyable. Please do remember to complete the feedback form that's posted in the chat box to receive your certificates. Thank you all for your active participation and for contributing to the success of this event. We look forward to welcoming you to our future sessions. Thank you, one and all.
Thank you.
you minimize DMA using MNT. So നമുക്ക് ഇവിടെ ഒരു മിനിമൽ DFA ആണ് ജനറേറ്റ് ചെയ്യേണ്ടത്. സോ ആദ്യമേ നമുക്ക് കമ്പൈൻ ചെയ്യാണ് ചെയ്യുന്നത്. അപ്പം A B വരും, അത് അൺമാർക്ഡ് റിസെക്റ്റ് ആണ്.